Hi, I'd like to talk about visualizing more in your neuroimaging data and the benefits this has for your own study as well as cross-study comparisons. Images are really the most important part of any scientific presentation, whether that's a talk, a poster, or a paper. In neuroimaging, when we present brain results, we normally show them like this, where we apply one or more thresholds, and then we show the small amount of voxels or clusters that survive that thresholding, and nothing else, even though we've usually acquired data throughout the whole brain and modeled it there. This is done with good intentions, but it introduces some troubling mathematical bias and leaves a lot of ambiguity and misinterpretation within a study, and also harms reproducibility and meta-analytic methods for cross-study comparisons. So I'd like to try to convince you today of why you should use transparent thresholding instead. As a bonus feature, we're going to talk about the NARPS data quite a lot. This is something that's often brought up as evidence of troubling amount of reproducibility crisis within the field, but actually there's some good news that there's a good amount of reproducibility in it as long as you visualize it appropriately. So in summary, I want to try to convince you that this is not really results, and we'll try to figure out a better way to create our results, with apologies to Renee Magritte. Actually, the original painting from which this is based is called The Treachery of Images, appropriately enough, and we're going to try to avoid having treacherous images that undermine our science and our results. This project is part of a large collaboration with a lot of people listed here, trying to promote better results reporting and reproducibility, so thanks to everyone here. Okay, what are results in a study? Well, currently the standard is to say that something like this is the results, where we apply maybe 2 levels of thresholding, and then we only show results there that passed both levels of thresholding. Everywhere else throughout the brain, we hide away. We show nothing there. All we know is that it's subthreshold. It could be P of 0.0011 or FWE of 5.1%, and it doesn't matter. We don't know anything about it. This hides quite a lot of information, and even if our focus is going to be on the main suprathreshold clusters here, we don't see any other context around them. We're treating everything else as if no activity happened there. And this is even the case, even though we know that often we're studying networks and that a given region like this might actually overlap with one or more functional networks spread throughout the brain, but we know nothing about those. So an alternative to this is to present results in this way with transparent thresholding. So this goes back to a study by Allen et al. In 2012, and here we show results everywhere. The suprathreshold ones are outlined and highlighted, and they're opaque, and results that are below the threshold actually are also shown with coloration. It's just that they fade as the statistics value falls lower and lower below the threshold. And as you can see here with the kind of fading, we're mostly seeing where results are near threshold and they fade away as you get towards 0 with the statistic. So this allows us to see the full context around the cluster still, and really we can see the kind of relative roles either across the network or other subthreshold regions quite usefully. There have been a lot of efforts over the years to try to promote showing more than just suprathreshold results in a study, and there's a lot of very good ideas. We're going to focus on this one because in my view it provides the nicest balance of distilling the results, kind of boiling them down, making them understandable and focused, while preserving a useful amount of information so we don't lose too much. It's easy to implement, so again, suprathreshold results are opaque and outlined, and those that are below threshold become more and more transparent. So where there are bright colors, they're near threshold, and then they fade away toward 0. What are the consequences of standard opaque thresholding? Well, there's a lot of very harmful ones, and we're going to focus on 3. One is it's unrealistic to biology. So brain regions aren't simply on and off. They have a lot of modulated responses. And we also know that in most cases, the brain regions themselves, or the responses we measure with the Bold effect, aren't simply on and off spatially. it's also bad statistics to treat subthreshold regions as having no effect or zero effect, which is what opaque thresholding does. This leaves a lot of the brain hidden away in a lot of other parts of a network that we may be seeing a main cluster in. And so this leaves a lot of room for ambiguity and misinterpretation and what we'll refer to as over-reducing results. And finally, the brain responses are a continuum, and this kind of thresholding is going to create instability in our results. So if we just change a small parameter like add or subtract a subject or change the blur value by a little bit or something like that, that we might see very strong differences in our results. And this artificially also impacts our ability to have reproducibility. It biases our results specifically toward non-reproducibility. Okay, so let's talk about ambiguity and clarity and how thresholding is affected by that. Before we get into neuroimaging, I want to go back to a kind of famous statistical example called Anscombe's quartet. So these plots all have the exact same set of summary statistics, mean, standard deviation, and correlation. Obviously, though, we can see that the underlying data is very different patterns here. So when it comes time to present our results or interpret it, if we only looked at the summary statistics, just the correlation or the mean and standard deviation, and then we try to picture the data or what it means or extrapolate from it, we're going to run into a problem, because from the same set of summary statistics, you get very different possible underlying data sets, and we have no idea which one of these it is, and it would really matter which one it is to how we interpret the data. So if we only report the summary statistics, we're left with a lot of troubling ambiguity and likely misinterpretation. We might picture this in our mind when the data is actually that or any of these or other ones. So what that means is, if we really want to interpret our data meaningfully, both for ourselves and when we tell others about it, if we include an image there, if we show the plots, we see useful context and kind of underlying results that helps us accurately understand and evaluate the data. So it breaks the ambiguity by presenting enough results and not over-reducing them. Okay, do we have this problem in neuroimaging? Well, let's go back to that first case that we looked at here of our lateralized cluster that we see here. There's no cluster here, so that's our interpretation with standard opaque thresholding. But we see that if we apply transparent thresholding, that there's more information there, and actually, it doesn't look so lateralized. The response looks fairly symmetric. But it's entirely possible that our underlying data, when we looked at it transparently, could have looked like this, where there's actually an anti-symmetric response. Or the underlying data from that single cluster could have looked like this, where there really is a lateralized response. Or the data could have looked like this, where there's a likely artifact present or something like that. So indeed, while all these four data sets have the same opaque thresholding result, we see that there's really a very different underlying biological context in all of them. And if we only present the opaquely thresholded cluster result, we have no idea which one of these four very different actual biological underlying data sets is present. So that's why we'd say that opaque thresholding over-reduces results and leads to a lot of ambiguity. We don't actually know what's happening in the data at a deeper level, and we're very likely to misinterpret it. Transparent thresholding instead keeps the context and allows us to have a much clearer and richer understanding. Okay, how does this affect cross-study comparisons? I mentioned before that we're going to use the NARPS data. So this was a public project that had a really interesting premise. So a single set of data was made public, and a large number of groups were made available to process it. So everyone, the different teams processed it independently, and there were over 60 of them, and then they responded yes or no about 9 specific hypotheses. This is often cited, the study, as evidence of a reproducibility crisis in neuroimaging because of how the responses didn't necessarily agree, or how there were a lot of no responses where there were maybe supposed to be yes. So let's look at how much of a reproducibility crisis this looks like. Well, the data was not presented like this in the original study, but if we look at each individual team's response for the same slice of data for the same hypothesis, which is what we're showing here, then when we look, we see that some of the results actually look like they agree pretty well. However, this one really looks like it doesn't agree with the other ones. Same with this one and this one. This one, some of the red blobs come and go. Down here, we see a red region where there's a blue one. So we might see that there's, or might say that there's a troubling amount of variability here because, again, this is all the same underlying data, just processed in different ways. Well, if we apply transparent thresholding, let's see what we think about the data. Okay, here. Now, if you look at this, what is your visual impression of the similarity now? If you look at this data set here, which remember before looked very different, what we see is when we apply transparent thresholding, it's not that it disagrees with the other data around it, it's that it agrees, it has the same hot, cold, hot pattern as all these other data sets around it. However, it just has lower statistical values. It is a very different thing to say that the data disagree in their results and findings than the fact that they agree just with different magnitude or size of response. So this is really the realm that we enter into in the different interpretations. Now, some of the data sets still do look very different, and we're able to see it. Actually, this set down here, this was something that was discussed in the original NARPS paper. What happened is actually a subset of teams presented their results with statistical findings that had exactly opposite sign usage. And this may be because some of the contrasts in the study were the negative effect of loss or the positive effect of loss. And so either people made a different choice about what sign convention to use or a mistake. These are actually understandable in a very particular way. So anyways, seeing more data with subthreshold results present really changes our interpretation in an important way. We can quantify that with similarity matrices, where if we apply with opaque thresholding, we use dice coefficients of overlap of clusters. And indeed, as we saw in like the first image, the positive clusters don't have a lot of overlap, and the negative clusters have some, but it's not really as much as you would expect from the same exact underlying data. And this might lead you to, as the original study wrote, substantial variability or findings of high levels of disagreement. However, in the transparent thresholding view, if you apply Pearson correlation, you actually see a huge amount of agreement across the bulk of the data sets. And as we discussed before, this cluster here that's highly correlated with itself and anti-correlated, these studies are actually understandable in the main context, and once you have a discussion about signs, these are probably all agreeing with this. And so the vast majority of these data sets agree fully, and there are a few that are very different from these, and that's fine. I don't think that's surprising, but overall, to me, this shows a huge amount of agreement and reproducibility. So what are we left with here? To me, the key finding from this study seems to be that the thresholding method is the key to evaluating reproducibility. It's not that the different amount of processing was the strongest effect. It was that the thresholding step just prior to meta-analysis made a huge difference, much more than the processing differences. So this should tell us that, hey, we should be very careful about thresholding and applying it before we try to evaluate reproducibility. And the main take-home message is here, to me, quite clearly, thresholding is very dangerous and biasing. Okay, let's take a look a little bit at that more about the stability and sensitivity to parameters that thresholding has. This is looking at one team's results of the NARPS data, different hypothesis, and when we apply opaque thresholding and see clusters, with the 47 subjects that were present after quality control, this is the group finding. There were 11 clusters, and here are some of them here. Now, if quality control maybe had been a little different, or if there were slightly fewer subjects in the data set, what do results look like? Well, with 46 subjects, now there are actually 13 clusters. So that's almost a 20% increase. And if the subjects reduced by one again, the number changed again. And if we reduce it, now it's actually reduced by quite a strong fraction. And if we keep reducing it, sometimes it changes, sometimes it doesn't. And if you notice here, watch this blue cluster, as I increase and decrease the subjects here, it goes away and comes back again. These are not purely monotonic changes of convergence. This are clusterized results. If these are all that we're going to present as our results, which is the realm we're in with standard opaque thresholding, our results are highly sensitive to our number of subjects, which is an arbitrary thing here just by changing by 1, and we don't want that property. What if we use transparent thresholding? Okay, well, now here we are at 47 subjects, and I'm going to continue to see what happens with 46, 45. The same number of clusters changes in the same way, but what do you notice? That the overall impression of the stability of the results is quite strong. The background context is not changing at all, and even though the cluster disappears, you still see it as a result. So the overall results here are much more stable. Sure, we can see that the clusters change, but we know that the clusters aren't really the only results here. The results are actually a much richer data set to draw from. Not only do we get increased stability, we see increased features, such as the fact that this blue cluster here actually has an almost symmetric partner here that is quite strong, though just subthreshold again. Is that meaningful? It appears probably to be, and this is something we could include in our interpretation, even if it's subthreshold. Okay, and again, we could try to quantify this using similarity matrices. As you might expect from what we looked at, the similarity with the number of subjects changing when we're in the opaque threshold, it decreases quite quickly, and this is actually an extended matrix, so the number of subjects decreases down to 17. By the time you're in the 20s, there's really quite low reproducibility. So this comparison after thresholding opaquely is very sensitive to n with large non-monotonic or kind of non-trivial changes. With transparent thresholding, we're in a very different regime of high stability, not sensitive to n, and we get the bonus of results with context in them. Okay, so hopefully this has shown many of the benefits, both within a study and cross-study, of transparent thresholding, and unfortunately many of the biases and detriments of opaque thresholding. A nice thing is, and one of the reasons this large consortium has gotten together, is to try to make it more readily findable to implement transparent thresholding in a larger number of packages. So some of these packages have had transparent thresholding for a very long time, and many of these have added it, though, very recently, or updated it and streamlined it. So you should be able to find transparent thresholding for your type of study, and whatever software you're comfortable with using. It's actually pretty easy to find, and so you should be able to implement it. Okay, so to summarize, I'd really like to consider data visualization as an important analysis step. It is not something that's done after the analysis or separate from it. How you threshold your data is a processing choice. It affects your meta-analysis, it affects your own interpretation of results. And so when you think about this question, what are my results? Please don't think about it this way, think about it this way. To me, it seems very convincing that this is much richer, and it avoids a lot of difficulties and problems with interpretation that this has. Again, standard thresholding has a lot of bias and ambiguity. Transparent thresholding shows the same superthreshold results. There's no information loss, but it adds context that can be discussed. And for cross-study comparisons, it avoids introducing a bias towards non-reproducibility, which we saw with the NARPS data, and transparent thresholding really allows us to see accurate comparisons. When things are similar, we can see it. When they're different, we can see it and actually understand the differences better. So this is good news. This is a step you can take towards improving reproducibility today. Thank you very much.